Continuing my introduction to surface metrology, today we'll be introducing linear and area scale. To do so, I'll first go over the basics, give an example, and how both are used in the lab. To start, we've got the basics. How you measure an object changes relative to how closely you look at it. This is the big idea of linear and area scale. It's the idea that as you look closer at an object, its surface changes, generally becoming much larger due to new mountains and valleys becoming apparent. Second most important idea is that linear and area scale are the same concept at different dimensions. Linear is two-dimensional and area is three-dimensional. Depending on the scale used, the same object can have a different relative length or area. This coincides with the first point, in that as you look closer at an object, its surface changes, becoming more textured. And lastly, different scales will be needed for particular applications. This is more for in the lab use and how we'll need to use different scales to find different correlations and discriminations between different surfaces. All right. Here's a graphic I made to help visualize length scale. Imagine for an instance the picture on the left is a short segment of a surface. To the naked eye, it looks flat and has a length represented in red. Taking a closer look at the section highlighted in the black box, the surface is actually much more textured. To accurately measure the length of the surface, each mountain and valley must be included. Doing so greatly increases the relative length of the original segment. In the lab, length scale doesn't get much use. It's mostly overshadowed by its big brother area scale. Speaking of, this is an example of area scale. In area scale, tiles are used as two-dimensional units to accurately measure surfaces. In the first picture, all the way on the right, tiles generally line up with the surface. As we move left and more tiles are added, the scale decreases and measurement becomes more precise, gradually increasing the relative area as the tiles come closer to matching the actual surface. If Vermont were flattened, it'd be the same size as Texas. One of Professor Brown's favorite sayings. Even though the lab ended up proving the statement false, it's still a good example of area scale. The premise is simple. Vermont is filled with mountains and valleys, while Texas is mostly flat. If each one of Vermont's mountains were flattened and squished out, its area would increase dramatically, almost in theory to that of Texas. This brings light to how measuring at a smaller scale can dramatically increase the relative area of an object. In the lab, area scale gets a lot of use. Mountains is one of our most used programs. It's used to calculate the area of surfaces at different scales by using triangular tiles. Area scale is used to correlate and discriminate between surfaces, seeing how characterizations change with scale. Length and area scale are clumped in with a bunch of other measurements to become what's known as multiscale. Lastly, noise, roughness, waviness, and form are common terms for different scales. So, thank you all for watching. I hope you enjoyed. I've been Connor. Until next time.